Tonight, we travel far, further than the asteroid belt, further than Jupiter's great storms, all the way to the sixth planet from our Sun, a world so beautiful, so strange, that astronomers throughout history could barely believe it was real. Saturn. For thousands of years, ancient civilizations watched this golden light wandering slowly across the night sky. They didn't know what it was. They couldn't have imagined that this quiet golden star was actually a giant world surrounded by thousands of rings made of ice and rock, stretching so wide they could fit 6 Earths inside them. But tonight, something is quietly changing. NASA's most powerful telescopes have just revealed something that scientists are still struggling to understand. Saturn is getting darker, slowly, silently, and we don't know how to stop it. Before we begin, if you found yourself here tonight, you're exactly where you need to be. Theories Before Sleep was built for minds that can't stop wondering, for people who fall asleep better when their thoughts are somewhere vast, somewhere beautiful, somewhere far beyond this world. Every night we release a new theory, a new mystery. Subscribe to Theories Before Sleep and turn on notifications. So every night, without fail, a new journey is waiting for you on your pillow. Now, get comfortable. Close your eyes. Tonight's theory is about to begin. This is Saturn, and something is deeply wrong. For generations, Saturn has been one of the most recognizable worlds in the night sky. A bright golden giant wrapped in soft bands of color, surrounded by rings that seem almost too perfect to exist. It has always felt stable, predictable, almost timeless. But now, when we place 2 modern images side by side, one from the James Webb Space Telescope and the other from the Hubble Space Telescope, that illusion begins to break. Because these are not just 2 pictures of the same planet. They are 2 completely different versions of Saturn. In visible light, Saturn still looks familiar, pale, striped, and calm. But in infrared, captured by Webb, the planet transforms into something darker, more complex, and far less stable than we expected. Entire regions fade into shadow. Atmospheric bands appear distorted. Heat signatures emerge where they shouldn't. And when you look long enough, you start to notice it. Saturn is dimming, not disappearing, not vanishing, but changing in a way that feels subtle at first and then impossible to ignore. This isn't about lighting. It's not just a difference in camera technology or wavelength. What we're seeing is deeper than that. These images are revealing layers of Saturn's atmosphere that were invisible before. And those layers are telling a story that doesn't match the Saturn we thought we understood. A story of shifting energy, of changing chemistry, of a system that may no longer be as stable as it once seemed. For the first time, we're not just observing Saturn as a distant object. We're analyzing it across multiple dimensions, comparing how it reflects sunlight, how it emits heat, and how its atmosphere behaves under different conditions. And when those pieces are combined, the result is unsettling. Because Saturn doesn't just look darker, it behaves differently. This matters more than it seems. Saturn is not just a planet. It is a massive, dynamic system, a balance of solar radiation, internal heat, chemical reactions, and atmospheric motion. Every color we see, every band, every glow is the result of that balance holding steady over time. So when that appearance changes, it suggests that something inside that system is shifting. And when something shifts on a planet this large, the consequences are never small. Scientists at NASA are now studying these differences with urgency. They're comparing years of observations, tracking brightness levels, mapping temperature variations, and trying to understand what exactly has changed and why now. Because this isn't just about Saturn looking different in a new telescope. It's about what those differences reveal. Is this part of a natural seasonal cycle? Something Saturn has always done, but we're only now able to see? Or are we witnessing a deeper transformation? Something happening inside the planet's atmosphere that could redefine how gas giants evolve over time. The truth is, we don't fully know yet, but what we do know is this: Saturn is not as constant as we once believed, and the more closely we look, the stranger it becomes, because beneath those rings, behind those clouds, something is changing, and for the first time, we're starting to see it. Before we can understand what's changing, we need to understand what Saturn is supposed to look like. Because for as long as we've been observing it, Saturn has been one of the most visually consistent planets in the solar system. Not static, but stable in its identity. When you think of Saturn, a very specific image comes to mind: a soft golden sphere, wrapped in gentle horizontal bands, surrounded by a vast glowing ring system. That image isn't an illusion. It's the result of a very precise balance of physics, chemistry, and sunlight. Saturn's iconic golden color comes primarily from its atmosphere, a deep layered envelope made mostly of hydrogen and helium, with traces of ammonia, methane, and water vapor. But those trace elements are what give Saturn its character. High in the upper atmosphere, ammonia condenses into tiny ice crystals, forming clouds that reflect sunlight. Below that, more complex hydrocarbons, created when ultraviolet radiation from the sun interacts with methane, produce hazes that scatter light in a way that softens and warms the planet's appearance. The result is that muted gold tone. Not bright like Jupiter's intense bands, and not blue like Neptune, but something more subtle, a diffused, almost glowing surface that feels calm and distant. This is what we've always considered normal Saturn, a planet where the colors are gentle, where the contrasts are low, where the atmosphere looks smooth, even though it's constantly in motion, because beneath that soft exterior, Saturn is anything but quiet. Winds in its upper atmosphere can reach speeds of over 1,800 kilometers per hour. Storm systems can span thousands of kilometers. Seasonal changes unfold over decades, driven by Saturn's long orbital period of nearly 30 Earth years. But despite all of that activity, the overall appearance remains surprisingly consistent. The bands shift, the storms come and go, the poles change with the seasons, yet the planet as a whole still looks like Saturn. And that consistency is important, because it tells us that, historically, the system has been in balance. Sunlight enters the atmosphere, interacts with gases and particles, and is reflected back into space in a predictable way. Heat from Saturn's interior rises through the atmosphere and escapes gradually, maintaining a stable thermal structure Everything works together, and when everything works together, the planet looks the way we expect it to look. But Saturn is not just its atmosphere. Its rings are what make it unforgettable. Discovered in detail by early telescopic observations and later revealed in extraordinary clarity by spacecraft like Cassini, Saturn's rings are one of the most complex and beautiful structures in the solar system. They are not solid. They are made of billions, possibly trillions, of individual particles ranging in size from microscopic ice grains to chunks as large as mountains. These particles are composed mostly of water ice, which makes them incredibly reflective. That reflectivity is why the rings appear so bright. When sunlight hits them, it scatters in all directions, creating that luminous, almost glowing halo around the planet. In visible light, the rings can sometimes outshine Saturn itself, depending on the angle and lighting conditions. And that's another key part of what we expect, because Saturn doesn't just exist as a planet. It exists as a visual system, planet plus rings, where light, shadow, and reflection all interact in a very specific way. As Saturn orbits the Sun, the angle of its rings relative to Earth changes. Sometimes we see them wide open, fully illuminated. Other times, during what's known as a ring plane crossing, they appear almost edge-on, becoming thin lines that nearly disappear. These cycles are predictable. They repeat over time, and they contribute to the idea that Saturn is a stable, almost clockwork-like world. Even the shadows behave as expected. The rings cast shadows on the planet's surface. The planet casts shadows onto the rings. These shadows shift with the seasons, creating patterns that scientists have studied for decades. And through all of it, Saturn maintains its identity. Bright, balanced, familiar. This is the Saturn we learned about. The Saturn captured in textbooks, in early telescope images, in the long, detailed observations from missions like Cassini, a world that changes, but only within known limits. So when scientists talk about Saturn getting darker, they're not comparing it to a random moment in time. They're comparing it to this baseline, to decades of consistent observation, to a planet that, despite its complexity, has always presented a relatively stable face to the universe. And that's why the recent images are so unsettling, because they don't just show variation, they show deviation, a difference that doesn't quite fit within the patterns we've come to expect. To understand why that matters, consider how sensitive Saturn's appearance is to its atmosphere. A small change in cloud composition can alter how light is reflected. A shift in temperature can change where clouds form. A variation in chemical reactions can darken or brighten entire regions. In other words, Saturn's appearance is a direct reflection of what's happening inside it. It's not just cosmetic, it's diagnostic. So when the planet looks darker, it suggests that something deeper is changing, something affecting how light moves through its atmosphere, how energy is distributed, how particles form, evolve, and interact. And that brings us back to what we expected. We expected Saturn to follow its cycles, to brighten and dim slightly with the seasons, to show storms and disturbances that come and go, to evolve slowly, predictably, over decades, but not to shift in a way that feels different, not to show contrast between wavelengths that are this stark, not to reveal layers that behave so differently from what we see on the surface. Because until now, The Saturn we saw was the Saturn we understood. But now, with instruments like the James Webb Space Telescope, we're no longer limited to what our eyes can see. We can observe heat. We can detect chemical signatures. We can look beneath the upper layers and study the deeper structure of the atmosphere. And when we do, the picture becomes more complicated because the normal Saturn, the golden, balanced, familiar world, may only be the surface of a much more dynamic and unstable system. A system that we're only just beginning to uncover. And that realization changes everything, because it means the Saturn we expected may never have been the full story at all. In March 2026, a new set of images was released. At first glance, they didn't seem revolutionary. Saturn had been photographed thousands of times before, by spacecraft, by ground-based observatories, and by orbiting telescopes that have been watching it for decades. But this time, something was different. For the first time, scientists had a clean, near-simultaneous comparison between two fundamentally different ways of seeing the same planet. One image came from the Hubble Space Telescope, capturing Saturn in visible light, the same spectrum our eyes perceive. The other came from the James Webb Space Telescope, observing Saturn in infrared wavelengths, where heat and deeper atmospheric layers become visible. Individually, each image made sense. But placed side by side, they told a different story, because the Saturn in those images didn't just look slightly different. It looked inconsistent. In the Hubble image, Saturn appeared as expected, pale gold with soft atmospheric bands and bright reflective rings stretching outward in clean symmetry. It was the Saturn we've always known, familiar, balanced. But in the Webb image, that same planet looked darker, not everywhere, but in key regions, especially across its equatorial zones and certain mid-latitude bands. The brightness dropped dramatically. Areas that should have reflected light appeared muted, almost suppressed. The rings, usually brilliant, seemed less dominant in contrast with the planet itself. And most striking of all, the atmosphere looked uneven. Instead of smooth transitions, there were abrupt changes, regions where heat signatures suggested energy was being redistributed in ways that didn't align with previous models. This wasn't just a difference in color. It was a difference in behavior, and scientists noticed it immediately. Within hours of the data being processed, researchers began isolating specific features. They compared brightness levels across wavelengths. They mapped thermal emissions. They overlaid historical datasets from previous years, and the conclusion came quickly. This wasn't just a visual artifact. Something had changed. The darkening wasn't uniform, which made it even more significant. If the entire planet had appeared darker, it could have been explained as a calibration issue or a global atmospheric shift. But this was selective, localized, structured. Certain bands absorbed more light than expected. Others emitted more heat than predicted. And when these regions were analyzed together, a pattern began to emerge, one that suggested a shift in how Saturn's atmosphere was interacting with both sunlight and internal energy. To understand why that matters, you have to consider how these images are constructed. Visible light images, like those from Hubble, show us reflected sunlight. They depend on how particles in the upper atmosphere scatter and reflect incoming radiation. Bright regions are highly reflective. Dark regions absorb more light. Infrared images, like those from Webb, tell a different story. They reveal heat, energy being emitted from the planet itself. Warmer regions glow brighter in infrared, while cooler regions appear darker. So when you compare the two, you're effectively comparing reflection and emission, surface appearance versus internal behavior. And in Saturn's case, those two layers no longer align perfectly. In some regions, the visible image suggests a relatively bright atmosphere, while the infrared image shows reduced heat emission. In others, the opposite is true. Darker visible regions correspond to unexpected thermal activity beneath. This mismatch is what caught scientists off guard, because it suggests that Saturn's atmosphere is no longer behaving in a simple, layered way. Instead, energy is moving differently, possibly more efficiently in some regions, possibly being trapped or redirected in others. And that leads to visible consequences. The darkening we see is not just a color change. It's a signal that something in Saturn's atmospheric system is shifting. The first reactions from the astronomy community reflected that uncertainty. Some researchers were cautious, suggesting that the differences could be seasonal, part of Saturn's long orbital cycle. After all, Saturn experiences seasons that last over 7 Earth years, driven by its axial tilt. Changes in sunlight distribution could alter cloud formation and atmospheric chemistry. But others pointed out that the magnitude and pattern of the darkening didn't fully match known seasonal behavior. Because Saturn has been observed through multiple seasons before, and while changes have been recorded, storms, color variations, even temporary disruptions, the overall structure of its appearance has remained relatively stable. This felt different, more complex, more layered. Some scientists propose that the darkening could be linked to changes in upper atmospheric haze, microscopic particles that influence how light is scattered. If those particles were decreasing in certain regions, it could reduce reflectivity, making those areas appear darker in visible light. But that alone wouldn't explain the infrared data. Others suggested that deeper atmospheric processes might be involved. Shifts in temperature gradients, changes in vertical mixing, or even variations in chemical composition at different altitudes. If warmer gases were rising or sinking differently than before, it could alter both the thermal structure and the visual appearance of the planet. And then there was another possibility, a more subtle but more profound one, that what we're seeing now isn't a sudden change, but the first time we're able to see something that has been evolving quietly for years. Because before the James Webb Space Telescope, our ability to observe Saturn in this level of infrared detail simply didn't exist. We were limited. We saw the surface, the clouds, the reflected light, but we couldn't fully map the energy beneath. Now we can. And what we're seeing suggests that Saturn's atmosphere may be far more dynamic and less stable than we once believed. The community response quickly shifted from surprise to focus. Observatories around the world began coordinating follow-up observations. Additional data from Hubble was requested. Ground-based telescopes were used to track changes over time. Historical datasets were reanalyzed, looking for early signs that might have been missed. Because if Saturn is changing, then the question isn't just what we're seeing now. It's when it started and how far it will go. One of the most striking aspects of the discovery was how visual it was. This wasn't a subtle shift buried in complex data. It was something you could see. Side by side, the difference was undeniable. A darker Saturn, a less reflective atmosphere, a planet that, for the first time, looked altered. And that visual impact mattered because it brought attention, not just from scientists, but from the public. Images of Saturn have always carried a sense of familiarity, a connection to something stable and distant. But these new images disrupted that perception. They made Saturn feel active, unpredictable, almost alive in its complexity. And that shift in perception is important because it reminds us that even the most familiar worlds are not static. They evolve, they change, sometimes slowly, over millions of years, and sometimes in ways we can suddenly see. The discovery in March 2026 didn't answer all the questions. It created them. Why is Saturn appearing darker in key regions? What processes are driving these changes? Are they temporary or part of a longer transformation? And perhaps most importantly, what else have we been missing? Because if Saturn, one of the most studied planets in our solar system, can still surprise us like this, then there may be entire layers of planetary behavior we've yet to understand. And now, for the first time, we have the tools to begin uncovering them. To understand why Saturn appears to be getting darker, we need to look beyond what we see on the surface, because the answer does not begin in the clouds, it begins in the rings. For a long time, Saturn's rings were thought to be stable structures, vast, bright, and almost permanent on human timescales. They seemed like a defining feature of the planet, something that had always been there and would always remain. But over the past decades, observations have revealed a different reality. Saturn's rings are slowly disappearing, not in a dramatic collapse, not in a sudden event, but through a quiet and continuous process that is happening right now. And as they disappear, they are affecting the planet itself. This process is known as ring rain. It is subtle, invisible to the naked eye, and yet powerful enough to reshape how Saturn looks from space. Saturn's rings are not solid. They are made of countless particles, mostly water ice, orbiting the planet at enormous speeds. Some are tiny grains of dust. Others are large chunks, even comparable in size to mountains. Together, they form the bright, reflective disk that makes Saturn so recognizable. But these particles do not stay in orbit forever. Saturn is surrounded by a strong magnetic field, an invisible structure that extends far into space. This magnetic field interacts with the particles in the rings in ways that slowly destabilize their motion. Ultraviolet radiation from the sun and impacts from micrometeoroids give these particles an electrical charge. Once charged, they no longer behave as simple orbiting objects. They begin to follow magnetic field lines, and those lines lead downward toward the planet. Over time, countless tiny particles leave the rings and fall into Saturn's upper atmosphere, not as droplets, not as visible streams, but as a continuous flow of charged material. This is ring rain. It is not a storm you can see. It is a process you can only detect through its effects. The first strong evidence for this came from the Cassini, which studied Saturn up close for more than a decade. Instruments on board detected unexpected chemical signatures in the upper atmosphere, including water-derived compounds that should not have been there in such quantities. The only plausible source was the rings. Material was falling from them into the planet, and it was happening on a massive scale. Estimates suggest that Saturn is losing thousands of kilograms of ring material every second. That may sound small compared to the total mass of the rings, but over long periods of time, it adds up. Over millions of years, it becomes transformation. Over tens of millions of years, it becomes disappearance. And according to current models, Saturn's rings may not last more than a few 100 million years. In astronomical terms, that is incredibly short, which means we are living at a very special moment, a moment where Saturn still has its rings, but is actively losing them. And that loss is not just happening in space, it is happening in the atmosphere. When ring material enters Saturn's upper layers, it changes the chemistry of the planet. Water and other compounds mix with the existing gases. This alters how clouds form. It changes how particles interact with sunlight. It affects how energy moves through the atmosphere. Saturn's familiar golden appearance depends on a delicate balance of scattering and reflection. Tiny particles in the atmosphere reflect sunlight back into space, giving the planet its soft, bright look. But when that balance is disturbed, the effect becomes visible. If fewer particles scatter light, more light is absorbed. If the composition of those particles changes, the way light behaves changes as well. The result is a reduction in brightness, a dimming. And over time, that dimming can become noticeable. This is one of the key reasons Saturn appears darker in recent observations. Not because the planet is losing light from the sun, but because its atmosphere is becoming less efficient at reflecting that light back into space. At the same time, ring rain affects temperature. When new material enters the atmosphere, it can influence how heat is absorbed, stored, and released. Some regions may trap heat more effectively, others may cool more quickly. This creates uneven thermal patterns across the planet, and those patterns are clearly visible in infrared observations from the James Webb Space Telescope. This is why Saturn looks different depending on how we observe it. In visible light, we see reduced reflection. In infrared, we see changes in heat distribution. Together, they reveal a planet that is no longer behaving in a uniform way. And that brings us to the second part of the story. Because Saturn is not only being changed by what is falling into it, it is also being changed by what it is losing. The rings themselves are becoming thinner, less dense, less reflective. Over time, they scatter less sunlight. They contribute less brightness to the overall system. Saturn, without its rings, would look very different, darker, simpler, less visually striking. And as the rings slowly fade, that transformation has already begun. Even small reductions in ring density can affect how light interacts with the planet. The rings reflect sunlight onto Saturn's atmosphere. They cast shadows that influence temperature. They act as part of a larger visual and physical system. As they weaken, that system shifts, the balance changes, and the result is subtle but real. Saturn begins to lose some of its brightness not just from within, but from its surroundings. This is not something that happens overnight. It is a gradual process, but with modern instruments, we can now detect it. We can compare past observations with present ones. We can measure changes in brightness. We can track how the rings evolve. And what we are seeing suggests that Saturn is in transition, a slow transformation that has been ongoing for a very long time, but is only now becoming visible to us. This is what makes the current moment so important. Because for the first time, we are not just observing Saturn as it is. We are observing Saturn as it changes. We are watching a planetary system evolve in real time, not over human timescales, but over scientific observation. And that changes how we think about it. Saturn is no longer just a symbol of stability. It is a system in motion, a planet shaped by its rings, and now, slowly, reshaped by their loss. The darkening we see is not a mystery without explanation. It is a signal, a visible consequence of processes that are deep, complex, and interconnected. Processes that involve magnetic fields, charged particles, atmospheric chemistry, and the slow decay of one of the most iconic structures in the solar system. And perhaps the most striking realization is this: what we are witnessing is not the end of Saturn's story. It is a chapter within it, a phase in the life of a planet that has existed for billions of years, a moment where change becomes visible, where the familiar begins to shift, and where a world we thought we understood reveals something new. To understand why Saturn appears darker today, we have to consider something subtle, something that changes so slowly it is almost invisible in real time. The angle, not just the angle of the rings, but the angle of the entire planet as it moves through space. Saturn is tilted on its axis, much like Earth. Its tilt is about 26.7 degrees, and that tilt controls how sunlight reaches the planet over time. But unlike Earth, Saturn takes nearly 30 years to complete a single orbit around the Sun. That means its seasons are stretched across decades. What looks like a small shift in angle to us is actually a long, slow transition in how energy is distributed across the planet. At certain points in its orbit, Saturn's rings are fully open to our view. They appear wide, bright, and reflective, catching sunlight and scattering it in all directions. In those moments, Saturn looks luminous, almost glowing, because the rings contribute significantly to the total brightness of the system. But as Saturn continues its journey, that angle changes. The rings begin to tilt. They narrow. Eventually, they approach a position where they appear almost edge-on from Earth. This moment is known as a ring plane crossing, and during this phase, the rings nearly disappear from view. When that happens, something important changes. The amount of reflected light drops dramatically. The rings, which once acted like massive mirrors, no longer contribute as much brightness. Instead of amplifying Saturn's glow, they fade into thin lines, offering very little reflection back toward us. And suddenly, Saturn looks different, darker, less radiant. But this is only the surface level effect, because the axial tilt does more than change what we see. It changes how Saturn itself behaves. As the angle of sunlight shifts, different regions of the planet receive different amounts of energy. One hemisphere may be bathed in sunlight for years, while the other remains in extended shadow. This imbalance drives atmospheric changes. Temperatures rise in sunlit regions and fall in shadowed ones. Chemical reactions speed up in some areas and slow down in others. Clouds form, dissipate, and reform in response to these changes. Over time, these differences accumulate. They reshape the atmosphere. Saturn's cloud system is layered and complex. At the top, there are thin hazes made of tiny particles formed through photochemical reactions. These hazes are responsible for scattering sunlight and giving Saturn its soft, muted appearance. Below that, there are ammonia ice clouds, which reflect a large portion of incoming sunlight. These clouds are one of the main reasons Saturn appears bright in visible light. Deeper still are more complex cloud layers, including water clouds and regions where temperature and pressure create entirely different chemical environments. Each of these layers depends on a balance of temperature, pressure, and chemical composition. When Saturn's tilt changes the distribution of sunlight, that balance begins to shift. In regions receiving less sunlight, temperatures drop. This can reduce the formation of certain cloud types or alter their structure. In regions receiving more sunlight, increased energy can drive stronger chemical reactions, producing new haze particles or changing existing ones. These changes are not uniform. They happen in patterns. Bands of atmosphere respond differently depending on latitude. Some zones brighten while others darken. Some regions develop thicker hazes while others become clearer. This creates contrast, and that contrast is exactly what modern observations are revealing. In visible light, certain parts of Saturn now reflect less sunlight than before. These regions appear darker, not because they are losing energy, but because they are no longer scattering light in the same way. At the same time, infrared observations show variations in heat distribution. Regions that appear dark in visible light may be warmer or cooler than expected, indicating that energy is moving differently through the atmosphere. This mismatch between visible and infrared data is one of the key clues. It tells us that the change is not just visual, it is physical. Something in the atmosphere is behaving differently. One possible explanation lies in the upper haze layer. If the density of haze particles decreases in certain regions, less light is scattered back into space. More light passes through, and the region appears darker. Alternatively, if the haze becomes more absorbing rather than reflective, it can trap light instead of scattering it, also leading to a darker appearance. Below the haze, changes in ammonia cloud formation can amplify this effect. If fewer ammonia ice crystals form, the atmosphere becomes less reflective. If clouds become thinner or more uneven, light is no longer distributed evenly across the surface. Even small changes in these layers can have large visual consequences, because Saturn's appearance depends on the combined effect of all these layers working together. Another factor is vertical mixing. Saturn's atmosphere is constantly in motion. Gases rise and fall, carrying heat and chemicals between layers. This mixing helps maintain a relatively uniform appearance over time. But if that mixing changes, the system becomes uneven. Some regions may receive more material from deeper layers, altering their composition. Others may become more isolated, allowing certain particles to accumulate or dissipate. This creates localized differences, and those differences show up as variations in brightness. The polar regions add another layer of complexity. Saturn's poles experience extreme seasonal changes due to the planet's tilt. They can spend years in darkness, followed by years in continuous sunlight. These transitions drive powerful atmospheric responses. At the North Pole, for example, the famous hexagonal storm structure persists, but the surrounding environment changes dramatically with the seasons. When sunlight returns after a long winter, chemical reactions intensify, creating new haze layers and altering cloud structures. These polar changes can influence the rest of the planet. Winds carry material from the poles toward lower latitudes. Temperature gradients shift. The entire atmospheric system adjusts. What begins as a seasonal effect at the poles can propagate across the planet. And when combined with changes in viewing angle, these effects become more visible to us. What we are seeing now may be the result of multiple processes overlapping. The rings contributing less reflected light due to their changing angle. The atmosphere responding to seasonal energy shifts, cloud layers forming and dissipating in new patterns, haze particles changing in density and composition. All of these factors interact. They do not act independently, and when they align in a certain way, the result is a noticeable change in how Saturn appears. It is important to understand that Saturn has always gone through cycles. These seasonal and atmospheric changes are not new in themselves. What is new is our ability to see them clearly. With advanced instruments like the Hubble Space Telescope and the James Webb Space Telescope, we can observe Saturn across different wavelengths, revealing layers that were previously hidden. We can compare how the planet reflects light and how it emits heat. We can track changes over time with greater precision. And when we do, we see a more complex picture, a planet that is not static but dynamic, not uniform but layered, not constant but evolving. The darkening of Saturn, then, is not a single event with a single cause. It is the visible outcome of a system in motion, a system influenced by its tilt, its orbit, its atmosphere, and its interaction with sunlight. What looks like darkness may actually be information, a signal that Saturn is changing in ways we are only beginning to understand. And as our ability to observe improves, that signal becomes clearer. Not because Saturn is suddenly different, but because we are finally seeing it as it truly is. To understand why Saturn can appear darker over time, we have to step into a timescale that feels almost unreal. Because on Saturn, winter does not last months, it lasts years. More precisely, each season on Saturn lasts around 7 Earth years. And when you combine the gradual transition into and out of that season, a hemisphere can experience nearly 15 years of reduced sunlight, a long descent into colder, darker conditions. This is not a temporary shift. It is a prolonged state, a slow, continuous change that reshapes the planet's atmosphere over time. Saturn's axial tilt, similar to Earth's, means that as it orbits the Sun, different hemispheres lean toward or away from sunlight. But because its orbit is so large, the transition between these positions is extremely slow. When a hemisphere begins to tilt away from the Sun, it does not suddenly enter darkness. It fades into it. Year after year, the amount of sunlight decreases. The angle of incoming light becomes shallower. Energy is distributed over a wider area, making it less effective at warming the atmosphere. Eventually, that hemisphere enters a deep seasonal winter. During this period, sunlight becomes scarce, temperatures drop, and the atmosphere begins to change. The first changes happen in the upper layers. Photochemical reactions, driven by sunlight, slow down significantly. These reactions are responsible for producing the haze particles that scatter light and give Saturn its soft, golden appearance. With less sunlight, fewer haze particles are created, and without those particles, the atmosphere becomes less reflective. Light is no longer scattered as efficiently. More of it is absorbed or passes through. Visually, this creates a darker appearance, but this is only the beginning. As the upper atmosphere cools, it affects the layers below. Cloud formation begins to shift. Ammonia clouds, which form when temperatures and pressures are just right, may become thinner or retreat to different altitudes. In some regions, they may dissipate altogether. Without these clouds, another layer of reflection is lost. The atmosphere becomes even less bright. At the same time, colder temperatures can stabilize certain parts of the atmosphere. Vertical mixing, the process that moves gases and heat between layers, can slow down. When this happens, the atmosphere becomes more stratified, more layered, and less dynamic in certain regions. This reduces the redistribution of particles that would normally maintain a balanced appearance. Instead, differences begin to build. Some areas retain more haze, others lose it. Some regions remain relatively bright, others grow progressively darker. Over time, this creates a patchwork of brightness and shadow across the planet. And because these changes happen slowly, they can go unnoticed until they reach a tipping point, a moment when the difference becomes visible, a moment when Saturn no longer looks the way we expect it to. The long winter also affects deeper atmospheric processes. Saturn generates heat from within. This internal energy rises through the atmosphere, interacting with the layers above. Under normal conditions, this creates a balance between incoming solar energy and outgoing thermal energy. But during extended winter, that balance shifts. With less solar input, the internal heat becomes relatively more important. It can create temperature gradients that differ from those seen during sunlit periods. These gradients influence wind patterns. They alter the movement of gases. They can even trigger large-scale storms. And when storms form, they can redistribute material across vast distances. They can bring deeper, darker material upward. They can disrupt existing cloud layers. They can leave behind regions that reflect light differently. All of these effects contribute to the overall darkening. What we see is not just a lack of light. It is the result of an atmosphere that has been reshaped by years of reduced energy input. The polar regions experience this most dramatically. At the poles, winter can mean continuous darkness for years at a time. During this period, the atmosphere undergoes extreme changes. Temperatures drop significantly. Chemical processes shift. New compounds can form, while others disappear. When sunlight eventually returns, it does not simply restore the previous state. It triggers a new phase, a phase of rapid change. Photochemical reactions resume, but now they act on an atmosphere that has evolved during the long winter. New haze particles form, sometimes with different properties than before. Cloud layers rebuild, but not necessarily in the same way. The result is an atmosphere that can look very different from one season to the next. This seasonal cycle is not perfectly symmetrical. Each transition leaves its mark, Each winter and summer reshapes the planet slightly, and over decades, these changes can accumulate. This is where modern observations become crucial. With telescopes like the Hubble Space Telescope and the James Webb Space Telescope, scientists can track these changes across multiple wavelengths. They can see how the atmosphere reflects light during different seasons. They can measure how heat is distributed. They can compare current data with observations from years or even decades ago, and what they are finding suggests that Saturn's current appearance may be strongly influenced by its position within this long seasonal cycle. The darkening we observe may not be a sudden anomaly. It may be the visible expression of a hemisphere emerging from or entering a prolonged winter phase, a phase where sunlight has been reduced for years, where atmospheric processes have adapted to that reduction, and where the planet's appearance reflects those changes. This does not mean that Saturn is permanently becoming darker. It means that it is moving through a cycle that unfolds over decades, a cycle that we are only beginning to observe in detail. But there is something important to understand. Even if this darkening is part of a natural cycle, it does not make it insignificant, because the scale of these changes is enormous. They involve entire hemispheres. They reshape atmospheric layers thousands of kilometers thick. They influence how energy moves through one of the largest planets in the solar system. And they remind us that even the most familiar worlds are not static. They are dynamic systems, constantly responding to their environment, constantly evolving. What we are seeing now is a snapshot of that evolution, a moment in Saturn's long seasonal rhythm, a moment where the balance of light and darkness has shifted, and for the first time, we have the tools to witness it clearly, to measure it, to understand it, and to realize that what appears as darkness is part of a much larger cycle, a cycle that has been unfolding for millions of years and will continue long after we are gone. To understand what is really happening to Saturn, we have to move beyond appearance, because what we are seeing is only the surface of a much deeper story, and that story is written in data. For decades, Saturn has been observed in visible light. We have studied how it reflects sunlight, how its clouds shift, how its rings shine against the darkness of space. But visible light only tells us one part of the story. It shows us how Saturn looks, not how it behaves. That is where infrared observations become essential. The James Webb Space Telescope does not see Saturn the way our eyes do. It detects heat. It reveals how energy moves through the planet's atmosphere. It exposes layers that are invisible in traditional images. And when Webb turned its instruments towards Saturn, the results were not just detailed, they were revealing. In infrared, Saturn does not appear as a smooth, golden sphere. It becomes a map of energy. Regions glow with varying intensity depending on their temperature. Bands that appear subtle in visible light become sharply defined. Areas that seem calm reveal underlying motion and imbalance. One of the first things scientists noticed in Webb's data was the uneven distribution of heat. Instead of a gradual transition from warmer to cooler regions, there were sharp contrasts. Some latitudes emitted significantly more infrared radiation than expected, while others appeared cooler or more subdued. This pattern did not fully match previous models. Because under stable conditions, Saturn's atmosphere should distribute heat more evenly over time. But the data suggested otherwise. It suggested that energy was being trapped in certain regions and released in others. This is important because it connects directly to the visual darkening. If a region traps more heat, it may also alter the formation of clouds and haze particles. Those changes can reduce reflectivity, making the region appear darker in visible light. At the same time, a region that loses heat more efficiently may cool enough to change its chemical balance, again affecting how it reflects light. In other words, the thermal structure revealed by Webb is closely tied to what we see in optical images. But the connection is not always straightforward. There are places where the visible and infrared data do not align. Regions that appear bright in visible light sometimes correspond to cooler areas in infrared. Other regions that look darker visually show unexpected heat signatures beneath. This mismatch is one of the most intriguing aspects of the data. It suggests that Saturn's atmosphere is layered in a way that is more complex than we previously understood. The upper layers may reflect light in one way, while deeper layers behave differently in terms of temperature and energy flow. This layered behavior creates a kind of disconnect, a planet that looks one way on the surface but behaves differently underneath. And that disconnect is exactly what we are seeing now. To better understand it, scientists compare Webb's data with observations from the Hubble Space Telescope. Hubble captures Saturn in visible and ultraviolet light, showing how sunlight interacts with the upper atmosphere. In these images, Saturn still retains much of its familiar appearance. The rings are bright and reflective. The atmospheric bands are soft and continuous. The overall tone is pale and balanced. But even in Hubble's data, subtle changes are visible. Some bands appear less distinct than before. Certain regions show reduced brightness. The contrast between different zones has shifted slightly. These are not dramatic changes, but they are measurable. And when placed alongside Webb's infrared observations, they become more meaningful because they reveal two perspectives on the same system. Hubble shows how Saturn reflects light. Webb shows how Saturn emits heat. Together, they provide a more complete picture, and that picture suggests that Saturn's atmosphere is undergoing changes that affect both reflection and emission. To see how significant these changes might be, scientists look further back in time. They compare modern data with observations from earlier missions. One of the most important of these is Voyager 1. When Voyager 1 flew past Saturn in 1980, it captured some of the first high-resolution images of the planet. These images became a reference point, a snapshot of Saturn as it appeared over 4 decades ago. In those images, Saturn looks remarkably uniform. The golden color is consistent. The bands are smooth. The overall brightness is stable across large regions. There are variations, of course, but they fit within a predictable pattern. Comparing those images to modern observations reveals both continuity and change. The fundamental structure of Saturn's atmosphere is still there. The bands still exist. The rings still dominate the system. But there are differences, subtle shifts in brightness, changes in contrast, variations in how certain regions reflect light. These differences are not dramatic when viewed in isolation, but when combined with the detailed data from Webb and Hubble, they become part of a larger trend. A trend that suggests Saturn's atmosphere is not static. It evolves, slowly but continuously. And over decades, those small changes can become significant. One of the key challenges in interpreting this data is separating natural variation from meaningful change. Saturn has always experienced storms, seasonal shifts, and fluctuations in its atmosphere. So how do we know that what we are seeing now is different? The answer lies in consistency. By comparing data across multiple wavelengths and multiple time periods, scientists can identify patterns that persist beyond short-term variations. They can track how certain regions behave over time. They can measure changes in brightness and temperature with increasing precision. And what they are finding is that some of the current observations do not fully match historical expectations. This does not mean that Saturn is undergoing a sudden transformation, but it does suggest that we are observing a phase of its evolution that may be more complex than previously understood. Another important aspect of Webb's data is its ability to detect specific wavelengths associated with certain molecules. Different gases emit and absorb infrared radiation in characteristic ways. By analyzing these signals, scientists can infer the composition of Saturn's atmosphere. Preliminary analyses suggest variations in the distribution of certain compounds, including those related to water and hydrocarbons. These variations could be linked to processes like ring rain or seasonal changes. They could also indicate shifts in atmospheric circulation. Either way, they provide additional evidence that the system is dynamic and that the darkening we observe is connected to real physical processes. The combination of all these datasets creates a layered understanding. Voyager provides the historical baseline. Hubble shows the visible present. Webb reveals the hidden structure beneath. Together, they form a timeline, a progression from what Saturn was to what it is becoming. And that progression is still unfolding. What makes this moment unique is not just the data itself, but the ability to compare it in real time. For the first time, we can observe Saturn across multiple wavelengths simultaneously. We can see how changes in temperature correspond to changes in brightness. We can track how different layers interact. We can begin to understand the system as a whole, and what we are learning is that Saturn is more complex than we imagined. Its atmosphere is not just a series of clouds. It is a dynamic system where energy, chemistry, and motion are constantly interacting, where small changes can ripple outward and become visible on a planetary scale. The darkening of Saturn is not a single event that can be explained by one factor. It is the result of multiple processes, each contributing in its own way. The data does not point to a simple answer, but it does point to a deeper understanding, a recognition that even a planet as familiar as Saturn can still surprise us, and that with every new observation, we are not just seeing more, we are seeing differently. What once appeared stable now reveals subtle shifts. What once seemed uniform now shows variation, and what once felt predictable now carries uncertainty. This is the power of data. It transforms observation into insight. It turns images into understanding. And in the case of Saturn, it is showing us a planet that is not fading quietly, but evolving in ways we are only beginning to comprehend. To understand how fast Saturn is changing, we need to do something that was impossible until recently. We need to measure time on a planetary scale, not seconds, not days, but years, decades, because Saturn does not change in ways that are immediately obvious. It evolves slowly, quietly, and for a long time, that made it seem almost constant. But now, with decades of accumulated observations, scientists can compare Saturn across time with a level of precision that was never possible before. And what they are finding is something subtle but important. Saturn is changing, and it is changing faster than we once thought. When researchers compare images from the 1980s, including those from Voyager 1, with modern observations from the Hubble Space Telescope and the James Webb Space Telescope, they can track variations in brightness across different regions of the planet. These comparisons are not based on what the eye sees alone. They involve calibrated measurements of reflectivity, known as albedo, and detailed analysis of how light interacts with Saturn's atmosphere. Over time, certain patterns emerge. Some regions have become slightly darker, others have brightened. The contrast between bands has shifted. At first, these changes appear minimal, a few percent difference in brightness, a slight variation in color tone. But on a planetary scale, even a small percentage is significant, because it represents a change in how billions of square kilometers of atmosphere are interacting with light. More importantly, these changes are not random. They follow patterns that suggest underlying processes. One of the key observations is that Saturn's brightness does not change at a constant rate. It accelerates and slows, depending on where the planet is in its orbit. During certain phases, especially when a hemisphere is entering or emerging from a long seasonal period, changes can become more noticeable over relatively short timescales. In some cases, measurable differences have been observed within just a few Earth years. That may not sound fast, but for a planet that takes nearly 30 years to orbit the Sun, it is. It means that what we are seeing now is not a static snapshot. It is part of an ongoing transition, a phase where multiple factors are aligning: seasonal changes, atmospheric adjustments, ring-related processes, all interacting at the same time. And when they do, the rate of visible change increases. Infrared data from the James Webb Space Telescope adds another layer to this understanding. By measuring how heat is distributed across Saturn's atmosphere, scientists can detect shifts that are not immediately visible in optical images. These thermal changes can occur more rapidly than visible changes. Heat can move, redistribute, and create gradients over shorter periods. And when these thermal shifts influence cloud formation and chemical reactions, they eventually translate into visible differences. This creates a kind of delay. The atmosphere changes internally first. Then, over time, those changes become visible on the surface. This means that the darkening we observe today may actually be the result of processes that began years ago, possibly even decades. What we are seeing is the visible phase of a longer transformation, a delayed response to changes that have been building over time. This raises an important question. If Saturn is darkening now, how long will it continue? Is this a temporary phase or something more permanent? To answer that, scientists look at cycles. Saturn's atmosphere is influenced by its long seasonal cycle, driven by its axial tilt and orbit. Each hemisphere goes through extended periods of sunlight and darkness. Clouds form and dissipate. Haze layers build up and break down. These cycles repeat over decades, and they provide a framework for understanding change. In this context, some of the darkening we observe may be temporary, a result of Saturn being in a specific phase of its seasonal cycle. As the planet continues its orbit, sunlight will shift. Regions that are currently darker may receive more energy. Atmospheric processes may reverse or adjust. Brightness may increase again. But not all changes are cyclical. Some processes operate on much longer timescales. Ring rain, for example, is a gradual and continuous process. It does not reverse. Material lost from the rings is not returned. Over time, this leads to a permanent reduction in ring mass. And as the rings thin, their contribution to Saturn's overall brightness decreases. This is not a seasonal effect. It is a long-term evolution. Similarly, changes in atmospheric composition can have lasting impacts. If certain chemical processes alter the balance of particles in the atmosphere, those changes may persist beyond a single seasonal cycle. They may become part of a new baseline, a new normal for how Saturn looks. This is what makes the current observations so complex. They are likely the result of both temporary and permanent processes. Some aspects of the darkening may fade with time, others may continue. And distinguishing between the two is one of the main challenges scientists face. Another factor to consider is feedback. Saturn's atmosphere is a system where changes can reinforce themselves. For example, if a region becomes darker and absorbs more sunlight, it may warm slightly. That warming can alter cloud formation, which can further reduce reflectivity, which leads to more absorption, and so on. This feedback loop can amplify changes, turning small variations into more noticeable differences. But feedback can also work in the opposite direction. Cooling can increase cloud formation, which increases reflectivity, which reduces absorption, which leads to further cooling. These competing processes create a dynamic balance, a system that is constantly adjusting, never fully stable, never completely predictable. This is why Saturn's darkening cannot be described as a simple trend. It is not a straight line from bright to dark. It is a complex pattern of fluctuations, driven by multiple interacting factors. To better understand the rate of change, scientists also look at shorter-term observations. They monitor Saturn over months and years, tracking how specific regions evolve. These observations show that while some changes are gradual, others can occur more quickly. Storm systems can alter cloud structures in a matter of weeks. Localized temperature changes can shift patterns over months. These short-term events are layered on top of long-term trends, adding complexity to the overall picture. But even with all this data, there is still uncertainty, because Saturn is a system that operates on timescales longer than a human lifetime. We are observing only a small part of its story, a fragment of its evolution. And yet, even within that fragment, we can see change. We can measure it, we can analyze it, and we can begin to understand it. What we know so far suggests that Saturn's darkening is not a sudden transformation. It is not an immediate collapse or a rapid shift. It is a gradual process, one that unfolds over years and decades. But within that gradual process, there are moments where change becomes visible, moments where multiple factors align, moments like the one we are in now. Whether this phase will continue or reverse remains an open question. But what is certain is that Saturn is not static. It is evolving, and we are witnessing that evolution in real time, not as a dramatic event, but as a slow, unfolding process, one that challenges our assumptions and deepens our understanding. Because the more we study Saturn, the more we realize that even the most familiar worlds are still full of surprises, still capable of change, still revealing new layers of complexity. And in that sense, the question is not just how fast Saturn is darkening. It is how much more there is to discover. Because if this is what we can see now, then the future of Saturn may hold changes we have not yet imagined. To understand what Saturn's darkening really means, we have to step back, far beyond the clouds, beyond the rings, beyond even the planet itself. Because Saturn is not just an isolated world. It is part of a larger story, a story about how planetary systems form, evolve, and eventually change. And right now, Saturn is showing us something rare. We are watching a planet lose one of its defining features, not in theory, not in simulation, but in real time. Saturn's rings are not permanent. They are temporary structures formed at some point in the planet's past and now slowly fading away. For decades, scientists believed these rings could be ancient, possibly as old as Saturn itself. But data from the Cassini changed that view. Measurements of the ring's mass, composition, and interaction with Saturn's atmosphere suggested something surprising. The rings are relatively young, possibly only 100 to 400 million years old. That means they may have formed long after Saturn itself, perhaps from the breakup of a moon, or from debris that failed to form into a stable satellite. Whatever their origin, the key point is this: they are not meant to last forever, and now they are disappearing, slowly, continuously, and inevitably. As ring rain pulls material down into Saturn's atmosphere, the rings lose mass. Particles collide, fragment, and drift. Some are pushed outward, many fall inward. Over time, the structure becomes thinner, less dense, less reflective, and eventually, it will fade. Current estimates suggest that Saturn's rings could largely disappear within 100 million years. In some models, significant fading could occur even sooner. On a human timescale, that feels unimaginably distant. But on a cosmic scale, it is the blink of an eye, which means something remarkable. We are living during the era of Saturn's rings, a brief window in the planet's lifetime where they exist, where they shine, where they define what Saturn looks like, before they vanish. And when they do, Saturn will change completely. Without its rings, Saturn would look like a different planet, still massive, still surrounded by clouds, still dynamic and complex, but no longer iconic, no longer instantly recognizable. The bright, reflective halo would be gone. The shadows cast by the rings would disappear. The interplay of light and structure that defines Saturn's appearance would vanish. What remains would be a gas giant, simpler, darker, and less visually distinct. But the implications go beyond appearance. Because Saturn's rings are not just decoration. They are part of a system. They influence the planet's environment. They reflect sunlight back toward the atmosphere. They interact with the magnetic field. They feed material into the upper layers through ring rain. As they disappear, all of these interactions weaken. The balance changes. Saturn's atmosphere evolves in response. Its brightness shifts. Its thermal structure adjusts. In other words, the loss of the rings is not just a visual transformation. It is a physical one, a change in how the planet functions. And this has implications beyond Saturn, because Saturn is not the only planet with rings. Other gas giants in our solar system also have ring systems. Jupiter, Uranus, and Neptune all possess rings, but none are as large or as bright as Saturn's. This raises an important question. Why is Saturn's ring system so prominent and so temporary? The answer may lie in timing. Ring systems may form and disappear throughout a planet's life. They may be created by collisions, by tidal disruptions, or by the capture of material, and over time, they decay. If that is true, then what we see around Saturn today may be just one phase in a repeating cycle. A phase that other planets have experienced or will experience in the future. This means that Saturn is not just losing its rings. It is revealing something about how planetary systems evolve. It is showing us that even large, stable-looking structures can be temporary. That change is not the exception. It is the rule. Looking even further, Saturn's rings may also be connected to processes that occur during the early formation of solar systems. When planets form, they are surrounded by disks of gas and dust. These disks can resemble rings. Over time, material clumps together to form moons, planets, and other structures. In a sense, Saturn's rings may be a miniature version of those early disks, a remnant of processes that shaped the solar system billions of years ago. And as they disappear, they offer a glimpse into both the past and the future. The past, where such structures were common, and the future, where they fade away. The timeline of this disappearance is still uncertain. Different models produce different estimates. Some suggest that most of the visible ring material could be gone within 100 million years. Others allow for longer timescales, depending on how quickly material is lost and how the system evolves. But all models agree on one point. The rings are temporary. They are not stable over billions of years. They are in decline, and that decline is measurable. What makes this moment extraordinary is that we are able to observe it. We are not just inferring that rings disappear. We are seeing the process. We are detecting the material falling into Saturn. We are measuring changes in brightness. We are tracking the evolution of the system. This places us in a unique position, observers of a transformation that usually unfolds beyond human perception, and it changes how we think about the solar system. For a long time, the planets were seen as fixed, stable, unchanging on human timescales. But Saturn challenges that idea. It shows us that even the most familiar worlds are dynamic, that they evolve, that they lose and gain features over time, and that what we see today is only a snapshot, a moment in a much longer story. The darkening of Saturn is part of that story. It is not just a visual change. It is a sign, a signal that the system is shifting, that the balance between rings, atmosphere, and sunlight is evolving, and that evolution, will continue, long after the current phase has passed, long after the rings have faded. What will Saturn look like then? We can only imagine. A darker planet, without its luminous halo, a world that still holds storms, winds, and deep atmospheric processes, but presents a simpler face to the universe. Less dramatic, less iconic, but still alive with complexity. And perhaps, in that future, observers from another world might look at Saturn and see something different. Not a ringed giant, but a planet that once had rings. A planet that changed, just as we are seeing it change now. This is the bigger picture. Saturn is not just dimming, it is evolving. And in doing so, it is teaching us something fundamental, that even in the vast, slow-moving scales of the cosmos, nothing remains the same forever. To understand what Saturn is teaching us, we have to move beyond the idea of a single planet changing, because what we are witnessing is not just about Saturn. It is about how we understand gas giants as a whole. For a long time, gas giants were seen as stable systems, massive, slow-moving worlds where change happened, but only within predictable limits. Their atmospheres were active, their storms powerful, but their overall identity seemed constant. Saturn challenged that perception, but now it is redefining it. The idea that a gas giant can visibly change in brightness, structure, and behavior over relatively short astronomical timescales forces us to reconsider something fundamental. These planets are not static. They are dynamic systems that evolve continuously. And more importantly, they may evolve in ways we have not fully understood yet. Saturn's darkening is not just a local phenomenon. It is evidence that large-scale atmospheric systems can shift in response to multiple interacting factors. Ring loss, seasonal cycles, atmospheric chemistry, energy redistribution. All of these processes are interconnected, and if they can reshape Saturn's appearance, then similar processes may be happening on other gas giants as well. The difference is that Saturn makes those changes visible. Its rings amplify the effect. They reflect light, cast shadows, and interact with the atmosphere in ways that highlight even subtle variations. Other gas giants do not have that advantage, or rather, we do not have that advantage when observing them. Take Jupiter, for example. Jupiter is the largest planet in the solar system, and its atmosphere is far more energetic than Saturn's. It is dominated by powerful storms, jet streams, and massive structures like the Great Red Spot. At first glance, Jupiter appears more dynamic than Saturn, but in terms of long-term structural change, it has often been treated as relatively stable. However, closer observation tells a different story. Jupiter's bands have changed color over time. Storm systems have appeared and disappeared. The Great Red Spot itself has been shrinking for decades. These changes are not identical to what we are seeing on Saturn, but they point to the same underlying principle. Gas giant atmospheres are not fixed. They evolve. They respond to internal and external forces, and those responses can become visible over time. Now consider Uranus. For much of its history, Uranus was considered a quiet, almost featureless world. Its atmosphere appeared smooth and uniform, with very little visible activity. But as observational technology improved, especially with infrared instruments, scientists began to detect changes, cloud formations, seasonal variations, subtle shifts in brightness. Uranus, like Saturn, has a significant axial tilt. In fact, it is even more extreme. Its seasons are more dramatic, and as it moves through its orbit, its atmosphere undergoes changes that can take decades to fully unfold. These changes were not obvious at first, but with better data, they became clear, and that is the key. What we see depends on how we observe. Saturn is showing us that once we have the right tools, we can detect changes that were always there. Which brings us to Neptune. Neptune is often seen as the most distant and mysterious of the major planets. Its deep blue color and powerful winds make it unique. But like Uranus, it was once thought to be relatively stable in appearance. That assumption has also changed. Recent observations have shown that Neptune's brightness can vary over time. Cloud systems can form and dissipate. Atmospheric patterns shift. Even at the edge of the solar system, change is constant, and this leads to a powerful realization. Saturn is not an exception. It is an example of how gas giants behave when we observe them closely enough. An example of how complex and dynamic these worlds really are. But Saturn adds something more. It shows us how interconnected these processes can be. The rings are not separate from the atmosphere. They are part of the system. They influence it, they feed into it, they evolve with it. This kind of interaction may exist elsewhere in different forms. Other planets may not have bright rings, but they may have other external inputs. Dust from moons, material from space, magnetic interactions. All of these can influence atmospheric behavior, and all of them can lead to changes over time. When we extend this idea beyond our solar system, the implications become even larger. Astronomers have discovered thousands of exoplanets, many of which are gas giants. Some are much larger than Jupiter. Others orbit very close to their stars, experiencing extreme temperatures. These planets are often studied using infrared data, similar to what the James Webb Space Telescope provides. And in many cases, scientists observe variability, changes in brightness, shifts in atmospheric composition, differences in heat distribution. Until recently, these variations were difficult to interpret. Were they noise, measurement errors, or real changes? Saturn helps answer that question. It shows us that variability is real, that gas giant atmospheres can change in measurable ways, that what we see in exoplanet data may reflect genuine physical processes. In this sense, Saturn becomes a reference point, a nearby laboratory where we can study these processes in detail, a place where we can connect theory with observation, and use that understanding to interpret distant worlds. This changes how we approach planetary science. Instead of assuming stability, we begin with variability. Instead of looking for constant conditions, we look for change. We ask new questions. How quickly do gas giant atmospheres evolve? What drives their variability? How do internal and external factors interact? And perhaps most importantly, how common are these changes? Are all gas giants evolving in similar ways? Or is each one unique? The answer is likely somewhere in between. There are shared principles, common physical laws that govern how atmospheres behave. But there are also differences. Each planet has its own composition, its own history, its own set of influences. Saturn's rings make its changes more visible. Jupiter's storms make its dynamics more obvious. Uranus and Neptune reveal their changes more slowly, more subtly. but all of them are part of the same broader picture, a picture of planets that are alive with motion, alive with change, and constantly evolving. This perspective also affects how we think about the future. If Saturn's rings are disappearing, what will Saturn look like in millions of years? If Jupiter's storms continue to evolve, how will its atmosphere change? If Uranus and Neptune go through extreme seasonal cycles, what long-term transformations might they undergo? These are no longer abstract questions. They are grounded in observation, in data, in real changes that we can measure, and they remind us of something fundamental. The solar system is not a static collection of objects. It is a dynamic system, a network of interactions, processes, and transformations. Saturn's darkening is one piece of that system, a visible sign of deeper changes, a clue that helps us understand the larger whole. And perhaps the most important lesson is this: what we see today is not permanent. It is a moment, a phase in the life of a planet. And just as Saturn is changing now, other worlds are changing as well, some in ways we can see, others in ways we have yet to detect. But all of them are part of the same story, a story of motion, of transformation, of a universe where even the largest, most familiar worlds are never truly still. To understand what happens when Saturn's rings disappear, we have to look at something often overlooked: the moons. Because Saturn's rings are not separate from its moons. They are deeply connected. In fact, the rings and the moons form a single system, a delicate gravitational dance that has been shaping Saturn for millions of years. And when the rings fade, that dance will change. Saturn has more than 80 known moons, ranging from tiny fragments to massive worlds like Titan and Enceladus. Some of these moons orbit far from the rings, barely interacting with them. But many exist within or near the ring system itself. And these moons are not passive. They actively shape the rings. Small moons embedded within the rings act as sculptors. They carve gaps. They create waves. They shepherd particles into narrow bands. These are known as shepherd moons, and their gravity keeps certain parts of the rings sharply defined. Without them, the rings would spread out and lose their structure much more quickly. But the relationship goes both ways. The rings also affect the moons. They provide material. They influence orbital dynamics. They create a constant exchange between solid bodies and orbiting particles. One of the most striking examples of this interaction is Enceladus. Enceladus is a small, icy moon, but it plays a massive role in Saturn's system. Beneath its frozen surface lies a subsurface ocean, and from cracks in its crust, jets of water vapor and ice particles erupt into space. These plumes feed Saturn's E-ring, one of the outer diffuse rings of the system. In other words, the rings are not just losing material, they are also being replenished, at least partially. But this balance is temporary. Over long timescales, the loss outweighs the gain, and as the rings continue to fade, the interaction between moons and rings will weaken. For moons embedded within the rings, the change will be immediate. As ring material disappears, the environment around them becomes less dense. The constant bombardment of particles decreases. The gravitational interactions with nearby ring matter diminish. This could alter their orbits slightly, not dramatically, but enough to change their long-term evolution. The structures they maintain, gaps, waves, edges, will begin to blur. Eventually, they may disappear entirely. The moons will remain, but the features they create will not. For larger moons outside the main rings, the effects are more subtle, but still significant. The rings act as a source of material and energy. They reflect sunlight. They scatter particles. They interact with Saturn's magnetosphere. As they fade, all of these interactions weaken. This changes the environment in which the moons exist. Take Titan, for example. Titan is a world with a thick atmosphere, lakes of liquid methane, and complex weather systems. While it orbits far from the main rings, it is still part of the broader Saturnian system. Changes in the rings can influence the distribution of particles and energy throughout that system. Over long periods, this could subtly affect Titan's environment, not in ways that would be immediately visible, but in ways that accumulate over time. Another important factor is the exchange of material. Some of Saturn's moons are coated with fine particles that originate from the rings. This material can alter their surfaces, changing their brightness, composition, and thermal properties. As the rings disappear, this source of material will diminish. Moons that once received a constant stream of icy particles will no longer be refreshed in the same way. Their surfaces may darken, their reflectivity may change, they will evolve differently. Then there is the question of origin. Some scientists believe that Saturn's rings may have formed from the destruction of a moon, a collision or tidal disruption that tore a satellite apart, spreading its material into orbit. If that is true, then the rings themselves are the remnants of a moon, and as they disappear, that material does not vanish. It falls back into Saturn, or it spreads outward, potentially interacting with other moons. In this sense, the disappearance of the rings is not just a loss. It is a redistribution. Material moves from one part of the system to another. Energy shifts. Gravitational relationships adjust. The entire system evolves. One of the most fascinating aspects of this evolution is how it affects stability. The rings currently act as a kind of buffer. They absorb impacts. They redistribute energy. They create a dynamic environment that influences nearby orbits. As they fade, that buffer weakens. Moons may become more exposed to external influences. Micrometeoroid impacts, gravitational perturbations, long-term orbital drift. These effects are small, but over millions of years, they can lead to significant changes. The architecture of Saturn's moon system could slowly shift. Orbits could adjust, interactions could change, new resonances could form, all as a result of the rings disappearing. But perhaps the most profound change is visual. Saturn's moons are often seen against the backdrop of the rings. The rings provide context, scale, contrast. They make the system feel unified. Without them, the scene changes completely. Saturn becomes a simpler planet. Its moons become more isolated. The sense of a connected system fades. Future observers, millions of years from now, might see Saturn as just another gas giant with a collection of moons. They would not see the rings. They would not see the structures we recognize today. They would not know that this system once looked so different, unless they had the data, unless they had the record. And that is where we are unique. We are observing Saturn at a time when its rings still exist, when its moons are still interacting with them, when the system is in a transitional phase, a phase that will not last forever. This gives us a rare opportunity. to study not just a static system, but an evolving one, to see how moons and rings influence each other, to understand how planetary systems change over time, and to capture a moment that future observers may never witness. Because when Saturn's rings are gone, its moons will remain, but their story will be different. A story without the bright, icy structures that once defined their world. A story shaped by what has been lost and what has taken its place. To understand where Saturn is going, we have to look at what comes next, because what we've seen so far, the darkening, the changing atmosphere, the fading influence of the rings, is only the beginning. The real story is what happens from here, and for the first time we are entering a phase where Saturn is no longer just a destination for exploration. It is a system under continuous observation, a world we will keep watching year after year, decade after decade. The era of flybys is over. The era of long-term observation has begun. After the end of the Cassini mission in 2017, Saturn was left without an orbiting spacecraft. For a moment, it seemed like the most detailed chapter of its exploration had come to a close. But in reality, it marked a transition. Because while Cassini gave us proximity, new technologies are giving us something different: continuity. Telescopes like the Hubble Space Telescope continue to monitor Saturn in visible light, tracking seasonal changes, storm activity, and variations in brightness over time. And now, the James Webb Space Telescope has added an entirely new dimension: infrared vision, the ability to see not just how Saturn looks, but how it behaves, how heat moves, how energy is distributed, how deep atmospheric layers interact with the surface. And Webb is only getting started. Unlike a spacecraft mission with a fixed timeline, Webb can observe Saturn repeatedly over many years. Each observation adds to a growing data set, a timeline of change, a record of evolution. With each new image, scientists can compare Saturn to its past self. They can track how regions darken or brighten. They can measure how temperatures shift. They can identify patterns that only become visible over time. This is something we have never had before: a continuous, multi-wavelength view of a gas giant in motion. And that continuity is what will allow us to answer the questions raised by the current observations. Is Saturn's darkening temporary? Is it part of a seasonal cycle? Or is it the beginning of a longer transformation? Webb will help us find out. But Webb is not the only piece of the future. Because even though there is no dedicated Saturn orbiter currently in operation, new missions are already in development that will indirectly expand our understanding of the Saturn system. One of the most important of these is the Dragonfly mission. Dragonfly is not going to Saturn itself. It is going to Titan, Saturn's largest moon. But that does not make it separate from the story, because Titan is deeply connected to Saturn's system. It orbits within the gravitational and magnetic influence of the planet. It interacts with the surrounding environment. And by studying Titan up close, Dragonfly will provide new insights into the broader Saturnian system. Dragonfly is designed as a rotorcraft, capable of flying through Titan's thick atmosphere and landing in multiple locations. It will analyze surface composition, atmospheric chemistry, and environmental conditions. And while its primary focus is Titan, The data it collects will help scientists understand how material and energy move within the Saturn system as a whole. It will add context, depth, detail. At the same time, proposals for future missions to Saturn itself are being actively studied. Concepts for new orbiters, atmospheric probes, and even missions targeting the rings directly are under consideration. These missions aim to answer questions that Cassini could not fully resolve. Questions about the origin of the rings, their exact composition, their rate of loss, and their long-term evolution. Some concepts involve sending probes into Saturn's atmosphere to directly measure its composition and structure. Others focus on high-resolution mapping of the rings and their interaction with the planet. While none of these missions have been launched yet, the scientific interest is strong because Saturn has become more than just a target of curiosity. It has become a key to understanding planetary systems, and that means it will remain a priority. In the meantime, Earth-based and space-based telescopes will continue to observe Saturn. Each year, new data will be added, new comparisons will be made, new patterns will emerge, and over time, those patterns will become clearer. We will begin to see how Saturn evolves across its seasons, how its atmosphere responds to changes in sunlight, how its rings continue to fade, and how all of these processes interact. The future of Saturn is not a single event. It is a timeline, a slow unfolding of changes that we can now track with increasing precision. And that is what makes this moment so important, because we are at the beginning of that timeline. We are seeing the first clear signs of change. We are asking the first questions, and we are building the tools that will allow us to answer them. In the years ahead, Webb will continue to observe Saturn in infrared, revealing details that were previously hidden. It will track temperature variations. It will map atmospheric dynamics. It will detect chemical signatures. And it will do so with a level of sensitivity that allows even subtle changes to be measured. At the same time, Hubble will continue to provide visible light observations, offering a consistent reference point. Together, these instruments will create a dual perspective: surface and depth, light and heat, appearance and behavior. And that combination will be critical, because understanding Saturn requires both. It requires seeing what is visible and what is not. It requires connecting the surface to the underlying processes, and it requires time to observe, time to compare, time to understand. Looking further ahead, the possibility of new missions to Saturn means that we may once again have spacecraft in orbit around the planet. If that happens, the level of detail will increase dramatically. We will be able to study the atmosphere directly, to sample its composition, to measure its dynamics in real time, and to observe the rings from within the system. This would transform our understanding once again. But even without a new orbiter, the future is already unfolding, because the tools we have now are enough to reveal change, to track it, to analyze it, and to learn from it. Saturn is not going anywhere, but it is not staying the same either. And that is what makes its future so compelling. It is a world in motion, a system in transition, a planet that continues to evolve. And for the first time, we are able to follow that evolution as it happens, not as a distant, abstract concept, but as a real, observable process one that will continue to unfold long into the future, and one that will keep revealing new layers of complexity with every observation. Because Saturn's story is not ending, it is continuing, and we are finally in a position to watch it in real time. To understand Saturn's future, we have to confront a difficult question. Will we ever see Saturn without its rings in our lifetime? The short answer is no, but the longer answer is more complex, because even though the rings will not completely disappear anytime soon, they are already changing in ways we can observe, and in some moments, they can almost vanish. Saturn's rings are vast, but they are also incredibly thin. In many places, they are only tens of meters thick. When viewed from above, they look immense and bright, but when viewed edge-on, they nearly disappear. This is not a distant future scenario. It already happens. As Saturn orbits the Sun, there are moments when the angle of the rings aligns with Earth in such a way that we see them from the side. These events, known as ring plane crossings, occur roughly every 13 to 15 years. During these periods, the rings become so thin from our perspective that even powerful telescopes struggle to detect them. To the human eye, Saturn can look almost like a ringless planet, a pale sphere floating in space without its defining feature. This is the closest we will come in our lifetime to seeing Saturn without its rings. But this is only a visual effect. The rings are still there. They have not disappeared. They are simply hidden by geometry. The true disappearance of the rings is a much slower process. Based on current estimates driven by data from missions like Cassini, Saturn's rings could largely fade over the next 100 million years. That timescale places their complete loss far beyond human experience. No one alive today will see Saturn become permanently ringless, and yet we are still witnessing something meaningful. Because the disappearance does not happen all at once. It happens gradually, subtly. The rings are losing mass, their structure is evolving, their brightness is changing. These changes are small on human timescales, but they are real. And with modern instruments like the James Webb Space Telescope and the Hubble Space Telescope, we can detect them. We can measure the loss of material. We can track variations in reflectivity. We can observe how the rings interact with Saturn's atmosphere. In a sense, we are watching the early stages of their disappearance. Not the end, but the beginning of the end. And that creates a unique kind of perspective, because even though the full transformation is far away, we know it is happening. We know that the Saturn we see today is temporary, that its most iconic feature is not permanent, and that knowledge changes how we experience it. There is an emotional weight to that realization. Saturn has always been more than just a planet. It is a symbol of balance, of beauty, of structure in the solar system. Its rings are not just physical objects. They are part of how we imagine the cosmos. From the earliest telescopic observations to modern space missions, Saturn's rings have defined it. They have made it unique, recognizable, almost timeless. To imagine Saturn without them is to imagine a different solar system, a quieter one, a simpler one, without that bright sweeping structure cutting through space, without the shadows and reflections that make Saturn feel alive, without the visual contrast that sets it apart from every other planet. It would still be Saturn, but it would not feel the same. And that is what makes this story more than just scientific. It is about change. About the idea that even the most stable, familiar things can evolve. That nothing in the universe is truly permanent. Not even something as iconic as Saturn's rings. For future generations, Saturn will still be a remarkable world. It will still have its storms, its atmosphere, its moons. But at some point, far in the future, observers will look at Saturn and see something different. A planet without rings. A world that once had a defining feature and lost it. And unless they have access to the records we leave behind, they may never know what it once looked like. They may never experience the Saturn we see today. That thought changes how we view the present. It makes this moment feel rare, special, because we are living in the era of Saturn's rings. A brief window in the planet's long history. A moment where everything aligns. The rings exist. They are visible. They are bright. And we have the technology to observe them in incredible detail. We can study them, measure them, understand them, and appreciate them. Not just as objects, but as part of a story that includes formation, evolution, and eventual disappearance, the darkening of Saturn, the changes in its atmosphere, the loss of ring material. All of these are pieces of that story. They are signs that the system is evolving, that time is passing, that change is happening, even if we cannot see the final outcome. And perhaps that is what makes it so powerful. We are not witnessing the end. We are witnessing the process. The slow, continuous transformation of a world. A transformation that reminds us of something fundamental. The universe is not static. It is not fixed. It is always moving, always changing, always evolving. And sometimes, if we look closely enough, we can see that change as it happens, not in dramatic events, but in subtle shifts, in differences between images, in variations in light and heat, in the quiet fading of something that once seemed permanent. Saturn's rings will not disappear in our lifetime, but they are not the same as they once were, and they will not remain as they are forever. We are living in a moment of transition, a moment where we can observe both what Saturn is and what it is becoming. And that may be even more meaningful than seeing the end itself, because it allows us to understand, to connect, and to realize that even in the vastness of space, change is constant, and nothing, no matter how beautiful or familiar, lasts forever. At the beginning of this journey, we looked at two images, two versions of the same planet, one familiar, one slightly different, and at first the difference felt small, easy to overlook. But now, after everything we've seen, everything we've uncovered, those images feel different, because now we understand what they represent, not just a change in color, not just a difference in light, but a shift in a planetary system, a world that is evolving. Saturn is not disappearing, but it is not the same. Its atmosphere is changing. Its energy is shifting. Its rings are slowly fading, and all of it is connected. What once felt stable now feels dynamic. What once seemed permanent now feels temporary, and that changes how we see it. Because Saturn has always been more than just a planet. It has been a symbol of structure, of beauty, of something constant in a constantly changing universe. But now, We know the truth. Even Saturn changes, slowly, quietly, but undeniably. And that brings us to something deeper, something that goes beyond science. We are living in a very specific moment in time, a moment where Saturn still has its rings, where they are still bright enough to define the planet, where they still reflect sunlight and shape everything we see. But that moment will not last forever. Saturn is changing, and we are the last generation to see it like this. That doesn't mean the rings will vanish tomorrow, or even in 1,000 years. But it means that we are here, at the turning point, at the phase where change becomes visible, where the story shifts from stability to evolution. And that makes what we are seeing now incredibly rare, not just scientifically, but historically. Because millions of years from now, Saturn will look different. Its rings will be thinner, darker, possibly gone, and the version of Saturn we know today will exist only in data, in images, and in memory, which means this moment matters. The observations we make, the images we capture, the understanding we build, all of it becomes part of the record, a record of a world in transition. So the next time you see Saturn, whether in an image, through a telescope, or in your imagination, remember this: you are not just looking at a planet, you are looking at a moment in a much larger story, a story that is still unfolding, and one that we are only beginning to understand. If you found this journey fascinating, take a moment to subscribe, because this is just one chapter in a much bigger universe. There are more mysteries waiting, more worlds changing, more discoveries that challenge everything we think we know. And if you have a theory about what's happening to Saturn, or what it might look like in the future, share it in the comments, because the conversation is just beginning. And in the next video, we're going even deeper into a question that changes everything. What if Saturn's rings are not just disappearing, but were never meant to last at all?